Welcome to Classification in Machine Learning. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Classification is probably one of the most widely used tools in machine learning in today's world. It is also one of the simpler versions to start understanding how a lot of machine learning works. We're going to start by taking a look at what exactly is classification, the important terminologies around classification. We'll look at some real-world applications, my favorite, popular classification algorithms, and there are a lot out there, so we're only going to touch briefly on a variety of them so you can see how the different flavors work. And we'll have some hands-on demos in Python embedded throughout the tutorial. Classification. Classification is a task that requires the use of machine learning algorithms to learn how to assign a class label to a given data. You can see in this diagram we have our unclassified data. It goes through a classification algorithms, and then you have classified data. It's hard to just see it as data, and that really is where you kind of start and where you end when you start running these machine learning algorithms and classification. And the classification algorithms is a little black box in a lot of respects. And we'll look into that. You can see what I'm talking about when we start swapping in and out different models. Let's say we are given the task of classifying a given bunch of fruits and vegetables on the basis of their category, i.e. fruits are to be grouped together and vegetables are to be grouped together. And so we have a data set, we'll call it the bunch, is divided into clusters, one of which consists of the fruits, while the other has the vegetables. You can actually look at this as any kind of data. When we talk about breast cancer, can we sort out in images to see what is malignant and what is benign? Very popular one. Can you classify flowers? The iris data set. Certainly in wildlife, can you classify different animals and track where they're going? Classification is really the bottom starting point or the baseline for a lot of machine learning and setting it up and trying to figure out how we're going to break the data up so we can use it in a way that is beneficial. So here the fruits and the vegetables are grouped into clusters, and each cluster has a specific characteristic, i.e. whether they are a fruit or a vegetable. And you can see we have a pile of fruits and vegetables. We feed it into the algorithm, and the algorithm separates them out, and you have fruits and vegetables. So some important terminologies before we dig into how it sorts them out and what that all means. When we look at the terminologies, you have a classifier. That's the algorithm that is used to map the input data to a specific category. The classification model, the model that predicts or draws a class to the input data given for training. Feature. It is an individual measurable property of the phenomena being observed. And labels, the characteristics on which the data points of a data set are categorized. The classifier and the classification model go together. A lot of times the classifier is part of the classification model. And then you choose which classifier you use after you choose which model you're using. Where features are what goes in, labels are what comes out. So your classifier model is right in the middle of that. That's that little black box we were just talking about. Clusters. They are a group of data points which have some common characteristics. Binary classification. It is a classification condition with two outcomes which are either true or false. Multi-label classification. This is a classification condition where each sample is assigned to a set of labels or targets. Multi-class classification, the classification with more than two classes. Here each sample is assigned to one and only one label. When we look at this group of terminologies, a few important things to notice. Going from the top, clusters, when we cluster data together, we don't necessarily have to have an end goal. We just want to know what features cluster together. These features then are mapped to the outcome we want. In many cases, the first step might not even care about the outcome, only about what data connects with other data. And there's a lot of clustering algorithms out there that do just the clustering part. Binary classification. It is a classification condition with two outcomes which are either true or false. We're talking usually it's either a cat or it's not a cat. It's either a dog or it's not a dog. That's the kind of thing we talk about binary classification. And then that goes into multi-label classification. Think of label as you can have an object that is brown. You can have an object that is labeled as a dog. So it has a number of different labels. That's very different than a multi-class classification where each one's a binary. You can either be a cat or a dog. You can't be both a cat and a dog. Real-world applications. So to make sense of this, of course, the challenge is always in the details, is to understand how we apply this in the real world. So in real-world applications, we use this all the time. We have email spam classifier. So you have your email inbox coming in. It goes through the email filter that we usually don't see in the background, and it goes, this is either valid email or it's a spam, and it puts it in the spam filter if that's what it thinks it is. Alexa's voice classifier, Google Voice, any of the voice classifiers, they're looking for points, so they try to group words together, and then they try to find those groups of words trigger a classifier. So it might be that the classifier is to open your tasks program or open your text program so that you can start sending a text. Sentiment analysis is really big. When we're tracking products, we're tracking marketing, trying to understand whether something is liked or disliked is huge. That's like one of the biggest driving forces in sales nowadays, and you almost have to have these different filters going on if you're running a large business of any kind. Fraud detection. You can think of banks. They find different things on your bank statement and they detect that there's something going on there. They have algorithms for tracking the logs on computers. They start finding weird logs on computers. They might find a hacker. I mentioned cat and dog. So here's our image classification. We have a neighbor who runs an outdoor webcam, and we like to have it come up with a classification when the wild animals in our area are out, like foxes. We actually have a mountain lion that lives in the area, so it's nice to know when he's here. Handwriting prediction, classifying A, B, C, D, and then classifying words to go with that. So let's go ahead and roll our sleeves up and take a look at some popular classification algorithms. Before we look at the algorithms, let's go back and take a look at our definitions. We have a classifier and a classification model. So we're looking at the classifier, an algorithm that is used to map the input data to a specific category. One of those algorithms is a logistic regression. The logistic regression is a classification algorithm used to model the probability of a certain class or event existing, such as pass, fail, or win, lose, etc. It provides its output using the logistic function or sigmoid function to return the probability value that can then be mapped to two or more discrete classes. A sigmoid function is an activation function that fits the variable and limit the output to a range between 0 and 1. A standard sigmoid function or logistic function is represented by the formula fx equals 1 over 1 plus e to the minus x, where x is the equation of the line and e is the exponential. Just taking a quick look at this, you can think of this as being a point of uncertainty. And so as we get closer and closer to the middle of the line, it's either activated or not. And we want to make that just shoot way up. So you'll see a lot of the activation formulas kind of have this nice S-curve where it approaches 1 and approaches 0. And based on that, there's only a small region of error. And so you can see in the sigmoid logistic function, the 1 over 1 plus e minus x to the minus x, you can see it frames that nice S-curve. We also can use a tangent variation. There's a lot of other different models here as far as the actual algorithm. This is the most commonly used one. Let's go ahead and roll up our sleeves and take a look at a demo that is going to use a logistic regression. So we're going to have the activation formula and the model, because you have to have both. For this, we will go into our Jupyter notebook. Now, I personally use the Anaconda Navigator to open up the Jupyter notebook to set up my IDE as a web-based. It's got some advantages that it's very easy to display in, but it also has some disadvantages in that if you're trying to do multi-threads and multi-processing, you start running into single get issues with Python, and then I jump to PyCharm. Really depends on whatever IDE you want. Just make sure you've installed NumPy and the sklearn modules into your Python in whatever environment you're working in so that you'll have access to that for this demo. Now, the team in the back has prepared my code for me, which I'll start bringing in one section at a time so we can go through it. Before we do that, it's always nice to actually see where this information is coming from and what we're working with. So the first part is we're going to import our packages. which you need to install into your Python, and that's going to be your NumPy. We usually use NumPy as in P. And then from sklearn, the learn model, we're going to use a logistic regression. And from sklearn metrics, we're going to import the classification report confusion matrix. And if we go ahead and open up the scikit-learn.org and go under their API, you can see all the different features and models they have. And we're looking at the linear model logistic regression, one of the more common classifiers out there. And if we go ahead and go into that and dig a little deeper, you'll see here where they have the different settings. And it even says right here, note, the regularization is applied by default. So by default, that is the activation formula being used. Now we're not going to spend, we might come back to this, look at some of the other models, because it's always good to see what you're working with. But let's go ahead and jump back in here, and we have our imports. We're going to go ahead and run those. So these are now available to us as we go through our Jupyter Notebook script. And they put together a little piece of data for us. This is simply going through 0 to 1. Actually, let's go ahead and print this out over here. We'll go ahead and print X just so you can see what we're actually looking for. And when we run this, you can see that we have our X is 0, 1, 2 through 9. We reshaped it. The reason for this is just looking for a row of data. Usually we have multiple features. We just have the one feature, which happens to be 0 through 9. And then we have our 10 answers right down here. 0, 1, 0, 0, 1, 1, 1, 1, 1, 1. You can bring in a lot of different data depending on what you're working with. You can make your own. You can, instead of having this as just a single, you could actually have like multiple features in here, but we just have the one feature for this particular demo. And this is really where all the magic happens right here. And I told you it's like a black box. That's the part that is kind of hard to follow. And so if you look right here, we have our model. We talked about the model right there, and then we went ahead and set it for library linear. As I showed you earlier, that's actually default, so it's not that important. Random state equals 0. This stuff you don't worry too much about. And then with the scikit-learn, you'll see the model fit. This is very common to scikit. They use similar stuff in a lot of other different packages, but you'll see that that's very common. You have to fit your data. And that means we're just taking the data and we're fitting our X right here, which is our features. That's our X. And here's Y. These are the labels we're looking for. So before we were looking at, is it fraud? Is it not? Is it cat? Is it not? That kind of thing. And this is looking at 0, 1, so we want to have a binary setup on this. And we'll go ahead and run this. You can see right here it just tells us what we loaded it with as our defaults, and that this model has now been created and we've now fit our data to it. And then comes the fun part. You work really hard to clean your data, to bake it and cook it. There's all kinds of, I don't know why they go with the cooking terms as far as how we get this data formatted. Then you go through and you pick your model, you pick your solver, and you have to test it to see, hey, which one's going to be best. And so we want to go ahead and evaluate the model. And you do this is that once you've figured out which one is going to work the best for you, you want to evaluate it so you can compare it to your last model. And you can either update it to create a new one or maybe change the solver to something else. I mentioned tangent. That's one of the other common ones that's commonly used with language. For some reason, the tangent, even though it looks almost to me identical to the one we're using with the sigmoid function, for some reason it activates better with language, even though it's a very small shift in the actual math behind it. We already looked at the data early, but we'll go ahead and look at it again just so you can see what we look at. We have our rows of 0, 1, row, it only has one entity. And we have our output that matches these rows, and these do have to match. You'll get an error if you put in something with a different shape. So if you have 10 rows of data and 9 answers, it's going to give you an error because you need to have 10 answers for it. A lot of times you separate this too when you're doing larger models. But for this, we're just going to take a quick look at that. The first thing we want to start looking at is the intercept, one of the features inside our linear regression model. We'll go ahead and run that and print it. You'll see here we have an intercept of minus 1.516. And if we're going to look at the intercept, we should also look at our coefficients. And if you run that, you'll see that we get our coefficient is the 0.7035. You can just think of this as your Euclidean geometry for a very basic model like this, where it intercepts the y at some point and we have a coefficient multiplying by it. A little more complicated in the back end, but that is the gist of this simple model with just the one feature in there. And we'll go ahead and we'll reprint the y because I want to put them on top of each other with the y predict. And so these were the y values we put in, and this is the y predict we had coming out. And you can see, here we go. There's the y actual, and there's what the prediction comes in. Now keep in mind that we used the actual complete data as part of our training. That is, if you're doing a real model, a big stopper right there, because you can't really see how good it did unless you split some data off to test it on. This is the first step, is you want to see how your model actually tests on the data you trained it with. And you can see here, there is this point right here where it has it wrong, and this point right here where it also has it wrong. And it makes sense because our input is 0 through 9, and it has to break it somewhere, and this is where the break is. So it says this half the data is going to be 0 because that's what it looked like to me if I was looking at it without an algorithm, and this data is probably going to be 1. And I forgot to point this out, so let's go back up here. I just kind of glanced over this window here where we did a lot of stuff. Let's go back and just take a look at that. What was done here is we ran a prediction. So this is where our predict comes in, is our model.predict. So we had a model fit. We created the model. We programmed it to give us the right answer. Now we go ahead and predict what we think it's going to be. There's our model.predict probability of X. And then we have our Y predict, which is very similar, but this has to do more with the probability numbers. So if you remember down below, we had the setup where we're looking at that sigmoid function. That's what this is returning. And the y predict is returning a 0 or a 1. And then we have our confusion matrix. We'll look at that. And we have our report, which just basically compares our y to our y predict, which we just did. It's kind of nice. It's simple data, so it's really easy to see what we're doing. That's why we use the simple data. This can get really complicated when you have a lot of different features and things going on and splits. So here we go. I printed out our actual and our prediction. So this is the actual data. This is what the predict ran. And then we'll go ahead and we're going to print out the confusion matrix. We were just talking about that. This is great if you have a lot of data to look at. But you can see right here our confusion matrix says, if you remember from the confusion matrix, we have the 2. This is 2 correct. 1, 2. And it's been a while since I looked at a confusion matrix. There's the 2, and then we have this one, which is our 6. That's where the 6 comes from. And then we have this one, which is the 1 false. This is the 2 1s, so we have this one here and this one here, which is misclassified. This really depends on what data you're working with as to what is important. You might be looking at this model, and if this confusion matrix comes up and says that you've misclassified even one person as being non-malignant cancer, that's a bad model. I wouldn't want that classification. I'd want this number to be 0. I wouldn't care if this false positive was off by a little bit more, as long as I knew that I was correct on the important factor that I don't have cancer. So you can see that this confusion matrix really aims you in the right direction of what you need to change in your model, how you need to adjust it. And then there's, of course, a report. Reports are always nice. If you notice, we generated a report earlier. We'll go and just print the report up, and you can remember this is our report. It's a classification report, y, y predict. So we're just putting in our 2 values. Basically what we did here visually with our actual and our predicted value. And we'll go ahead and run the report, and you can see it has the precision, the recall, your F1 score, your support, translated into accuracy, macro average, and weighted average. So it has all the numbers. A lot of times when working with clients or with the shareholders in the company, this is really where you start because it has a lot of data and they can just kind of stare at it and try to figure it out. And then you start bringing in like the confusion matrix. I almost do this in reverse as to what they show. I would never show your shareholders the intercept of the coefficient. That's for your internal team only working on machine language. But the confusion matrix and the report are very important. Those are the 2 things you really want to be able to show on these. And you can see here we did a decent job of classifying the data, managed to get a significant portion of it correct. We had our, was it accuracy here is a 0.80 F1 score, that kind of thing. So, it's a pretty accurate model. Of course, this is pretty goofy because it's a very simple model, and it's just splitting the model between ones and zeros. So that was our demo of the on logistic regression on there. Let's go ahead and take a look at k nearest neighbors. This one is another very highly used and important algorithm to understand. K nearest neighbors is a simple algorithm which stores all available cases and classifies new cases based on the similarity measure. The k nearest neighbor finds out the class of the new data point by finding its nearest neighbors. If there are 3 data points of class A and 2 data points of class B near to the new data point, then the KNN classifies the new data point as class A. The k in k nearest neighbors is the number of nearest neighbors we are looking for. i.e., if we say k equals 3, this means that we are looking for nearest 3 neighbors of unclassified data point. Usually we take the k value between 3 to 10 as it leads to a better result. A smaller value of k means that noise will have a bigger influence on the result, and a larger value of k makes it computationally expensive. Hence, the data scientists prefer the range of k between 3 and 10. When we talk about noise, you remember the data we just looked at was 0, 1, 1, 0, 0. It had some values where cut it and said everything to the right is a 1, everything to the left is a 0, but it had some 1s and 0s mixed in there. That's called noise. That's what they're talking about, is there's some things that are right in the middle in the classification, which makes it very hard to classify. So suppose we're trying to find the class for a new point indicated by the red color. And you can see it's kind of right between the cat, right between the dogs. Let k equal 3, so we are finding the 3NN for the red data point. By looking at the plot on the right, we can see that the red data point belongs to the class dogs, as it has 2 votes for class dog and 1 vote for class cat. And if you ask the question, well, what are you measuring the distance? What is that distance? It could be the measurements of the ears, whether they're pointed or floppy. That might be one of the features you're looking at, is how floppy the ears are. Another one might be the whiskers versus the nose. And then you take those measurements, and using one of the most common things in k-means measurement is the Euclidean geometry, you can figure out the distance between those points. There's a lot of different algorithms for that. But you can think about it that you do have to have some kind of solid data to measure. And so we can conclude that the new data point belongs to the class dog. So let's go ahead and see what this looks like in code and do a demo on the k nearest neighbors in here. And we'll go right back into our Jupyter notebook and open up a new Python programming script page. Of course, once we're in here, we'll want to look at the scikit-learn. I did just a quick search for sk neighbors, kn neighbors classifier. This actually is the older version, 0.023 is the one we want. And you'll see here that we have all their defaults. N neighbors equals 5. At defaults, we were talking about that between 3 and 10. There's different ways to weigh it. There's an algorithm based on it. I mentioned Euclidean geometry, finding the distance. There's other algorithms for figuring out what that distance is and how to weight those. And there's a lot of other parameters you can adjust. For the most part, the k-means basic setup is a good place to start, and just let the defaults go. We might play with some of those. We'll see what the guys in the back did. And from here we're going to import NumPy. We're going to use pandas. If you haven't been running pandas, pandas is our data frame which sits on top of NumPys. Data frames are, NumPys is our number array. Pandas is our data frame. Matplot library, because we're going to plot some graphs. Everybody likes some pretty pictures. It makes it a lot easier to see what's going on when you have a nice display. And that's also what the Seaborn is in here in the setup that sits on top of the Matplot library. The ones we really want to look at right here are what we're bringing in from sklearn. These ones right here. So from sklearn, we're going to load, I mentioned the breast cancer. That's a very popular one because it has, I believe it's 36 measurements, so there's 36 features, and unless you're a expert, you're not going to know what any of those features really mean. You can sort of guess, but there's special measurements they take of when they take an image. And of course our confusion matrix, so that we can take a look and see what the data looks like and how good we did. And then we have our KN neighbors classifier on here. And then I mentioned that whenever you do training and testing, you want to split the data up. You don't want to train the data and then test it on the same data. That just tells you how good your training model is. It doesn't tell you whether it actually works on unknown data. And so this just splits it off so that we can train it, and then we can take a look at data we don't have in there and see how good it did. And we'll go ahead and load our data up. So here's our setup on that. Oops, there we go. So we're going to go ahead and load the data up. We have our X value, and that's going to come from our breast cancer.data and column breast cancer feature names. So there's our actual, all our different features. We'll print that out here in a second. And then we have our mean area, mean compactness. So I guess we're going to take the data and we're only going to use a couple of the columns. This just makes it easier to read. Of course, when you actually we're going to do this, you'd want to use all your columns. And then we have our Y, and this is simply whether it's either malignant or benign. And then we want to go ahead and drop the first line because that's how it came in on there. And we'll go ahead, let's just take a look at this a little closer here. Let's go and run this real quick. And just because I like to see my data before I run it, we can look at this and we can look at the original features. Remember, we're only going to use 2 features off of here just to make it a little easier to follow. And here's the actual data, and you can see that this is just this massive stream of data coming in here. It's going to just skip around because there's so much in there to set up. I think there's like 500 if I remember correctly, and you can see here's all the different measurements they take. But we don't really need to see that on here. We're just going to take a look at just the 2 columns. And then also our solution. We'll go ahead and just do a quick print Y on here so you can see what the Y looks like. And it is simply just 0, 0, 0, benign, 0, 0, 0, 1. So 1 means it's benign, 0 means it's malignant. Is what we're looking at on that. Go ahead and cut that out of there. The next stage is to go ahead and split our data. I mentioned that earlier. We'll just go ahead and let them do the splitting for us. We have X train, X test, Y train, Y test, and so we go ahead and train, test, split, X, Y, random state equals 1. It makes it nice and easy for us. We'll go ahead and run that. And so now we have our training and our testing. Train means we're going to use that to train the model, and then we're going to use the test to see how good our model does. And then we'll go ahead and create our model. Here's our KNN model, the K neighbors classifier. N neighbors equals 5. The metrics is Euclidean. Remember I talked about Euclidean? This is simply your C squared equals A squared plus B squared plus A squared equals B squared plus C squared plus C squared plus D squared. And then you take the square root of all that. That's what they're talking about here. It's just the length of the hypotenuse of a triangle. But you can actually do that in multiple dimensions, just like you do in 2 dimensions with a regular triangle. And here we have our fit. This should start to look familiar since we already did that in our last example. That's very standard for scikit and any other one, although sometimes the fit algorithms look a little bit more complicated because they're doing more things on there, especially when you get into neural networks. And then you have your k-neighbors. It just tells you we created a k-neighbors setup. They kind of wanted us to reformat the y, but it's not that big of a deal for this. And it comes out and shows you that we're using the Euclidean metric for our measurement. So now we've created a model. Here's our live model. We fitted the data to it. We say, hey, here's our training data. Let's go ahead and predict it. So we're going to take our y predict equals KNN predict y test. So this is data we have not. This model has not seen this data, and so we're going to create a whole new set of data off of there. Now, before we look at our prediction, in fact, let's. I'm going to bring this down and put it back in here later. Let's take a look at our X test data versus the Y test. What does it look like? And so we have our mean area. We're going to compare it to our mean compactness. We're going to go ahead and run that. And we can see here the data, if you look at this, just eyeballing it, we put it in here, we have a lot of blue here, and we have a lot of orange here. And so these dots in the middle, especially like this one here and these here, these are the ones that are going to give us false negatives, and so we should expect this is your noise. This is where we're not sure what it is. And then B9 is, in this case, is done in blue, and malignant is done in 1. So if you look at it, there's 2 points based on these features, which makes it really hard to have 100% where the 100% is down here or up here. That's kind of the thing I'd be looking for when we're talking about cancer and stuff like that, where you really don't want any false negatives. You want everything, false positive, great. You're going to go in there and have another setup in there where you might get an autopsy or something like that done on it. Again, that's very data specific on here. So now let's go ahead and pull in and get our prediction in here, and we'll create our Y prediction. We'll go ahead and run that. So now this is loaded with what we think the unknown data is going to be, and we can go ahead and take that and go ahead and plot it, because it's always nice to have some pretty pictures. And when we plot it, we're going to do the mean area versus mean compactness. Again, you look at this map and you can see that there's some clear division here. We can clearly say on some of the stuff that our Y prediction, if we look at this map up here and this map down here, we probably got some pretty good deal. It looks pretty good, like they match a lot. This is, of course, just eyeballing it. Really, you don't want to eyeball these things. You want to show people the pictures so that they can see it and you can say, hey, this is what it looks like. But we really want the confusion matrix. And when we do the Y test and the Y predict, we can see in the confusion matrix here, it did pretty good. And we'll just go ahead and point that out real quick. Here's our 42, which is positive, and our 79. And if I remember correctly, I'd have to look at the data, which one of these is a false negative. I believe it's the 9. That's scary. I would not want to be one of those 9 people told that I don't have cancer and then suddenly find out I do. So we would need to find a way to sort this out. And there is different ways to do that. A little bit past this, but you can start messing with the actual Euclidean geometry and the activation measurements and start changing those and how they interact. But that's very advanced. There's also other ways to classify them or to create a whole other class right here of we don't knows. Those are just a couple of the solutions you might use for that. But for a lot of things, this works out great. You can see here, maybe you're trying to sell something. Well, if this was not life dependent, and this was, if I display this ad, 42 of these people are going to buy it. And if I display this other ad, if I don't display it, 79 people are going to go a different direction or whatever it is. So maybe you're trying to display whether they're going to buy something if you add it on to the website. In which case, that's really a good numbers. You've just added a huge number of cells to your company. So that was our K nearest neighbors. Let's go ahead and take a look at support vector machines. So support vector machines is the main objective of a support vector machine algorithm is to find a hyperplane in an n-dimensional space, n is the number of features, that distinctly classifies the data points. And if you remember, we were just looking at those nice graphs we had earlier. In fact, let me go ahead and flip back on over there. If we were looking at this data here, we might want to try to find a nice line through the data. And that's what we're talking about with this next setup. So the main objective of support vector machine algorithm is to find a hyperplane in an n-dimensional space. N is the number of features that distinctly classifies the data points. To separate the two classes of data, there are many hyperplanes that can be chosen. Our objective is to find the plane that has the maximum margin, i.e. the maximum distance between data points of both classes. The dimensions of the hyperplane depends on the number of features. If there are 2 input features, then the hyperplane is just a line. If there are 3 features, then the hyperplane becomes a 2-dimensional plane. The line that separates the data into 2 classes is called as support vector classifier, or hard margin. And that's what I just showed you on the other data. You can see here where we look for a line that splits the data evenly. The problem with hard margin is that it doesn't allow outliers and doesn't work with non-linearly separable data. And we just were looking at that. Let me flip back on over here. And when we look at this setup in here, and we look at this data, here we go. Look how many outliers are in here. These are all these blue dots on the wrong side of the line would be considered an outlier, and the same with the red line. And so it becomes very difficult to divide this data unless there's a clear space. There we go. Therefore, we introduce soft margins, which accept the new data point and optimize a model for nonlinear data points. Soft margins pass through the data points at the border of the classes. The support vector machine can be used to separate the 2 classes of shapes. Here we can see that although triangles and diamond shapes have pointy edges, but we are able to classify them in 2 categories using a support vector machine. Let's go ahead and see what that looks like in a demo. We'll flip back on over to our Jupyter notebook. We always want to start with taking a look at the sklearn API, in this case the SVM SVC there is a significant number of parameters because the SVM has been a lot of development in the recent years and it's become very popular. If we scroll all the way down to methods, you'll see right here is our fit and our predict. That's what you should see in most of the scikit-learn packages. So this should look very familiar to what we've already been working on. And we'll go ahead and bring in our import and run that. We should already have pandas, numpy, our matplot library, which we're going to be using to graph some of the things. A little bit different right here, you'll see that we're going to go ahead and bring in one of the fun things you can do with test data is make circles. Circles are really hard to classify. You have a ring on the inside and a ring on the outside, and you can see where that can cause some issues. And we'll take a look at that a little closer in a minute. Here's our SVM setup on there, and then of course our metrics, because we're going to use that to take a closer look at things. So we go ahead and run this. Whoops, already did. Once we've gone ahead and done that, we're going to go ahead and start making ourselves some data. And this part, probably a little bit more complicated than we need. I'm not going to go too much in detail on it. We're going to make a mesh grid, and we'll see what that looks like in a minute. We're defining the minimums. You can see in here, create a mesh grid of points. Here's our parameters of x, y, and h. It's going to return x, x, y, y. You can also send a note to us. Make sure you get a copy of this if you want to dig deeper into this particular code especially. And we have a ymin, ymax, ymin, ymax. +1. Here's our mesh grid we're actually going to make x, x, and y, y. Plot the contours all the way through. And this is just a way of creating data. It's kind of a fun way to create some data. We go plot contours AX, CLF, X, X, Y, Y. And return an out. Add some perimeters here so that when we're doing it, we have our setup on there, train property, and then we'll go ahead and make our data. Just throw that right in there too in the same setup and run that. So now we have x and y. We're going to make our circles. We have n samples equals samples. In this case, we're going to have 500 samples. We went ahead and gave it noise of 0.05, random state 123. These are all going into, oops, go back up. Here we go. Make our mesh grid, make circles. There it is. So this is going into our make circles up here. And this is part of that setup on this. And then once we've gone ahead and make the circle, let's go ahead and plot it. That way you can see what we're talking about. Right now what I'm saying is really confusing because without a visual it doesn't really mean very much what we're actually doing. So I'm going to go ahead and run this with the plot. And let's go back up here and just take a look. We've made our circle. We have our n samples equals samples. So we're going to have 500. We're going to have training property 0.8. Here's our data frame. We go and load it into the data frame so we can plot it. Groups, df group by label. This is kind of a fun way if you have multiple columns. You can really quickly pull whatever setup is in there. And then we go ahead and plot it. And you can see here we have 2 rings that are formed. And that's all this is doing, is just making this data for us. This is really hard data to figure out. A lot of programs get confused in this because there's no straight line or anything like that. But we can add planes and different setups on here. And so you can see we have some very interesting data. We have our zeros in blue and our ones in the yellow in the middle. And the data points are an XY coordinate plot on this. One of the things we might want to do on here is go ahead and find the min to max ratio set up in there. And we can even do, let's just do a print x so you can see what the data looks like that we're producing on this. There we go. So x equals x minus x min over x max minus x min. All we're doing is putting this between 0 and 1. Whatever this data is, we want a 0 to 1 setup on here. And if you look at this, all our data is 0.8, 0.5. That's what this particular line is doing. That's a pretty common thing to do in processing data, especially in neural networks. Neural networks don't like big numbers. They create huge biases and cause all kinds of problems. And that's true in a lot of our models. Some of the models it doesn't really matter, but when you're doing enough of these, you just start doing them. You just start putting everything between 0 and 1. There's even some algorithms to do that in the sklearn, although it's pretty, as you can see, it's pretty easy to do it here. So let's go ahead and jump into the next thing, which is a linear kind of setup. C equals 1.0. This is the SVM regularization parameter we're going to use. Models, here's our SVM. And let's go and scroll up just a notch. There we go. So here we are with our model. We're going to create the setup with the SVC. Kernel is linear. And we'll come back to that because that's an important setup in there as far as what our kernel is, and you'll see why that's so important here in a minute, because we're going to look at a couple of these. And so this one is, we're actually going to be changing how that processes it. And then our C, here's our 0.0, and then the rest of this is plotting. We're just adding titles, making the contours so it's a pretty graph. You can actually spend, this would be a whole class just to do all the cool things you can do with scatter plots and regular plots and colors and things like that. In this case, we're going to create a graph with a nice white line down the middle so that you can see what's going on here. And when we do this, you can see that as it split the data, the linear did just that. It drew a line through the data, and it says this is supposed to be blue and this is supposed to be red, and it doesn't really fit very well. And that's because we used a linear division of the data, and it's not very linear data on there. It's anything but linear. So when we look at that, it's like, well, okay, that didn't work. What's the next option? Well, there's a lot of choices in here. One of them is just simply we can change this from the kernel being linear to poly. And we'll just go back up here and use the same chart. Oops, here we go. So here we go, linear kernel. We'll change this to poly. And then when we come in here and create our model, here's our model up here, linear. We can actually just go right in and change this to the poly model. And if you remember, when we go back over here to the SVC, and let's scroll back up here, there's a lot of different options. Oops, even further. Okay, so when we come up here and we start talking about the kernel, here's the kernel. There's linear, there's poly, RBF, sigmoid, pre-computed. There's a lot of different ways to do this setup, and their actual default is RBF. Very important to note that. So when you're running these models, understanding which parameter really has a huge effect on what's going on. In this particular one with the SVM, the kernel is so important. You really need to know that. And we switched our kernel to poly, and when we run this, you can see it's changed a little bit. We now have quite an interesting looking diagram, and you can see on here it now has these classifications correct, but it messes up in this blue up here, and it messes up on this blue is correct, and this blue is supposed to be red. You can see that it still isn't quite fitting on there. And so that is, when we do a polyfit, you can see if you have a split in data where there's a group in the middle that's one kind of data and the groups on the outside are different, the polyfit or the polykernel is what's going to be fit for that. So if that doesn't work, then what are we going to use? Well, they have the RBF kernel. And let's go ahead and take a look and see what the RBF looks like. And let me go and turn, there we go, turn my drawing off. And the RBF kernel, oops, there we go, RBF. And then of course for our title, it's always nice to have it match with the RBF kernel. And we go ahead and run this, and you can see that the RBF kernel does a really good job. It actually has divided the data up on here, and this is the kind of what you expect here was that ring. Here's our inner ring and an outer ring of data, and so the RBF fits this data package quite nicely. And that, when we talk about SVM, it really is powerful in that it has this kind of sorting feature to it in its algorithms. This is something that is really hard to get the SK means to do, or the k-means setup. And so when you start looking at these different machine learning algorithms, understanding your data and how it's grouped is really important. It makes a huge difference as far as what you're computing and what you're doing with it. So that was a demo on the support vector. Certainly you could have continued on that and done like a confusion matrix and all that kind of fun stuff to see how good it was and split the data up to see how it vectorizes. The visual on that's so important. It makes a big difference just to see what it looks like and that giant donut and why it does circles so well, or your poly version or your linear version. So we've looked at some very numerical kind of setups where there's a lot of math involved, Euclidean geometry, that kind of thing. A totally different machine learning algorithm for approaching this is the decision trees. And there's also forests to go with the decision trees. They're based on multiple trees combined. The decision tree is a supervised learning algorithm used for classification. It creates a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. A decision tree is a hierarchical tree structure where an internal node represents features or attribute. The branch represents a decision rule, and each leaf node represents the outcome. And you can see here where they have the first one, yes or no, and then you go either left or right, and so forth. One of the coolest things about decision trees is, and I'll see people actually run a decision tree even though their final model is different, because a decision tree allows you to see what's going on. You can actually look at it and say, why did you go right or left? What was the choice? Where's that break? And that is really nice if you're trying to share that information with somebody else as to why. When you start getting into the why this is happening, decision trees are very powerful. So the topmost node of a decision tree is known as the root node. It learns to partition on the basis of the attribute value. It partitions the tree in a recursive manner. So you have your decision node. If you get yes, you go down to the next node. That's a decision node. And either yes, you go to, if it ends on a leaf node, then you know your answer, which is yes or no. So there's your end classification set up on there. Here's an example of a decision tree that tells whether I'll sleep or not at a particular evening. Mine would be depending on whether I have the news on or not. Do I need to sleep? No. Okay, I'll work. Yes. Is it raining outside? Yes, I'll sleep. No, I'll work. So I guess if it's not raining outside, it's harder to fall asleep where you have that nice rain coming in. And again, this is really cool about a decision tree is I can actually look at it and go, oh, I like to sleep when it rains outside. So when you're looking at all the data, you can say, oh, this is where the switch comes in. When it rains outside, I'll sleep really good. If it's not raining or if I don't need sleep, then I'm not going to sleep. I'm going to go work. So let's go ahead and take a look at that looks like in the code. Just like we did before, we go ahead and open up the scikit setup just to say what the decision tree classifier has. You have your parameters, which we'll look a little bit more in depth at as we write the code. But it has different ways of splitting it. The strategy used to choose a split at each node, criterion, max depth. Remember the tree, how far down do you want it? Do you want it to take up the space of your whole computer with and map every piece of data, or the smaller that number is, the smaller the level of the tree is and the less processing it takes, but it's also more general, so you're less likely to get as in-depth an answer. And then of course minimal samples you need for it to split, samples for the leaves. There's a lot of things in here as far as how big the tree is and how to define it and when do you define it and how to weight it. And they have their different attributes which you can dig deeper into. That can be very important if you want to know the why of things. And then we go down here to our methods, and you'll see just like everything else, we have our fit method, very important, and our predict. The two main things that we use, what we're going to predict our x to be equal to. And we'll go ahead and go up here and start putting together the code. We're going to import our numpy, our pandas, there's our confusion matrix, our train test split, decision tree classifier. That's the big one that we're actually working with. That's the line right here where we're going to be, decision tree, there it is. Decision tree classifier, that's the one I was looking for. And of course we want to know the accuracy and the classification report on here. And we're going to do a little different than we did in the other examples. And there's a reason for this. Let me go ahead and run this and load this up here. We're going to go ahead and build things on functions. And this is, when you start splitting up into a team, this is the kind of thing you start seeing a lot more, both in teams and for yourself, because you might want to swap one data to test it on a different data depending on what's going on. So we're going to have our import data here, the data set length, the balance, and so forth. This just returns balanced data. Let me just go ahead and print, because I'm curious as to what this looks like. Import data, and it's going to return the balanced data. So if I run that, if we go ahead and print this out here and run that, you can see that we have a whole bunch of data that comes in there, and some interesting setup on here has, let's see, BRR. I'm not sure exactly what that represents on here. 111, 112, and so forth. So we have a different set of data here. The shape is 5 columns, 1, 2, 3, 4, 5. It seems to have a number at the beginning, which I'm going to guess BRL, a letter I mean, and then a bunch of numbers in there. 1111. Let's see, down here we got 555 set up on this. And let's see, balanced data. And since it said balanced data, I'm going to guess that B means balanced, R means you need to move it right, and L means it's needs to be moved left or skewed to the left. I'm not sure which one. Let's go and close that out. And we'll go ahead and create a function to split the data set. X balance data equals data values. Y balance equals data values of 0. There's that letter. Remember, left, right, and balance. And then we're looking for the values of 1 through 5. And we go ahead and split it just like you would X train, Y train set, random state 100. Test size is 0.3, so we're taking 30% of the data. And it's going to return your X, your Y train, your X train, your X test, your Y train, your Y test. Again, we do this because if you're running a lot of these, you might want to switch how you split the data and how you train it. I tend to use a bifold method. I'll take a third of the data and I'll train it on the other 2/3 and test it on that third, and then I'll switch it. I'll switch which third is the test data. And then I can actually take that information and correlate it, and it gives me a really robust package for figuring out what the complete accuracy is. But in this case, we're just going to go ahead. This is our function for splitting data. And this is where it kind of gets interesting, because remember we were talking a little bit about the different settings in our model. And so in here, we're going to create a decision tree, but we're going to use the Genie setup. And where did that come from? What's the Genie on here? So if we go back to the top of their page, and we have what criterion are we going to use? We're going to use Genie. They have Genie and entropy. Those are the two main ones that they use for the decision tree. So this one's going to be Genie, and if we're going to have a function that creates the Genie model, and it even goes down here, and here's our fit train of the Genie model, we'll probably also want to create one for entropy. Sometimes I even just, I might even make this just one function with the different setups. And I know one of the things I worked on recently, I had to create one that tested across multiple models. And so I would send the parameters to the models, or I would send this part right here where it says decision tree classifier. That whole thing might be what I send to create the model, and I know it's going to fit. We're going to have our X train, and we're going to have our predict, and all that stuff is the same. So you can just send that model to your function for testing different models. Again, this just gives you one of the ways to do it. And you can see here we're going to train with the Genie, and we're also going to train with the entropy to see how that works. And if you're going to have your models going, two separate models you're sending there, we'll go ahead and create a prediction. This simply is our Y predict equals our whatever object we sent, whatever model we sent here, the CLF object, and predict against our X test. And you can see here print Y predict and return Y predict set up on here. And we'll load that definition up. And then if you're going to have a function that runs a predict and prints some things out, we should also have our accuracy function. So here's our calculate the accuracy. What are we sending? We're sending our Y test data. This could also be Y actual and Y predict. And then we'll print out a confusion matrix. Then we'll print out the accuracy of the score on here and print a report, classification report. Bundle it all together there. So if we bring this all together, we have all the steps we've been working towards, which is importing our data. By the way, you'll spend 80% of your time importing data in most machine learning setups and cooking it and burning it and getting it formatted so that it works with whatever models you're working with. The decision tree has some cool features in that if you're missing data, it can actually pick that up and just skip that and says, I don't know how to split this. There's no way of knowing whether it rained or didn't rain last night, so I'll look at something else, like whether you watched TV after 8 o'clock, that blue screen thing. So we have our function importing our data set. We bring in the data. We split the data, so we have our X test and Y train. And then we have our different models, our CLF Genie, so it's a decision tree classifier using the Genie setup, and then we can also create the model using entropy. And then once we have that, we have our function for making the prediction, and we have our function for calculating the accuracy. And then if we're going to have that, we should probably have our main code involved here. This probably looks more familiar if you're, depending on what you're working on. If you're working on like a PyCharm, then you would see this in throwing something up real quick in Jupyter Notebook. So here's our main data import, which we've already defined. We get our split data. We create our Genie. We create our entropy, so there's our two models going on here. There's our two models. So these are two separate data models. We've already sent them to be trained. Then we're going to go ahead and print the results using Gini index. So we'll start with the Gini, and we want to go ahead with the Gini and print our predictions, X test to the Gini, and calculate the accuracy on here. And then we want to print the results using entropy. So this is just the same thing coming down like we did with the Gini. We're going to put out our Y predict entropy and our calculations. So let's go ahead and run that and just see what this piece of code does. We do have, like, one of our data is getting a warning on there. That's nothing major because it's just a simple warning. Probably an update of a new version's coming out. And so here we are. We have our data set. It's got 625. You can actually see an example of the data set. B meaning balanced, I guess. And here's our 5 data points. 1, 1, 1, 1 means it's balanced. It's skewed to the right with 1, 1, 1, 2, and so forth on here. And then we're going to go ahead and predict from our prediction whether it's to the right or to the left. You can think of a washing machine that's banging on one side of the thing, or maybe it's an automated car where we're down the middle of the road that's in balance and it starts veering to the right, so we need to correct for it. And when we print out the confusion matrix, we have 3 different variables, R, L, and B. So we should see the 3 different variables on here. And you have, as far as whether it predicts, in this case, the balance. There's not a lot of balanced loads on here. And didn't do a good job guessing whether it's balanced or not. That's what I took from this first one. The second one, I'm guessing, is the right. So it did a pretty good job guessing the right balance. You can see that a bunch of them came up left unbalanced. Probably not good for an automated car, as it tells you 18 out of the 18 missed things and tells you to go the wrong direction. And here we are going the other way, 19 to 71. And of course we can back that up with an accuracy report on here, and you can see the precision, how well the left and right balance is, 79%, 79% precision, and so forth. And then we went and used the entropy, and let me just see if we can get, so we can get them both next to each other. Here's our entropy of our the first setup, our first model, which is the Gini model. 67, 18, 1971, 63, 22, 2070, pretty close. The 2 models, that's not a huge difference in numbers. This second one of entropy did slightly, it looks like slightly worse, because it did 1 better as far as the right balance and did, 4 worse on the left balance or whatever. So slightly worse. If I was guessing between these, I'd probably use the first one. They're so close, though, that it wouldn't be a clear choice as to which one worked better. And there's a lot of numbers you can play with here which might give better results depending on what the data is going in. Now, one of the takeaways you should have from the different category routines we ran is that they run very similar. You certainly change the parameters in them as to whether you're using, what model you're using and how you're using it and what data they get applied to. But when you're talking about the scikit-learn package, it does such an awesome job of making it easy. You split your data up, you train your data, and you run the prediction, and then you see what kind of accuracy, what kind of confusion matrix it generates. So we talk about algorithm selection. Logistic regression, k-nearest neighbors. Logistic regression is used when we have a binomial outcome. For example, to predict whether an email is spam or not, whether the tumor is malignant or not. The logistic regression works really good on that. You can do it in a k-nearest neighbors also. The question is, which one will it work better in? I find the logistic regression models work really good in a lot of raw numbers. So if you're working with, say, the stock market, is this a good investment or a bad investment? So that's one of the things that it handles the numbers better. K-nearest neighbors are used in scenarios where non-parametric, no fixed number of parameters, algorithms are required. It is used in pattern recognition, data mining, and intrusion detection. So K means really good in finding the patterns. I've seen that as a preprocessor to a lot of other processors where you use the k-nearest neighbors to figure out what data groups together. Very powerful package. Support vector machines. Support vector machines are used whenever the data has higher dimensions, the human genome microarray. SVMs are extensively used in the handwriting recognition models. And you can see that we were able to switch between the parabolic and the circular setup on there, where you can now have that donut kind of data and be able to filter that out with the support vector machine. And then decision trees are mostly used in operational researches, specifically in decision analysis to help identify a strategy most likely to reach any goal. They are preferred where the model is easy to understand. I like that last one. It's a good description. Is it easy to understand? So you have data coming in. When am I going to go to bed? Was it raining outside? You can go back and actually look at the pieces and see those different decision modes. It takes a little bit more to dig in there and figure out what they're doing, but you can do that, and you can actually help you figure out why. People love it for the why factor. So, strengths and limitations. Big one on all of these. The strengths and limitations, we talk about logistic regressions. The strengths are it is easy to implement and efficient to train. It is relatively easy to regularize the data points. Remember how we put everything between 0 and 1? When you look at logistic regression models, you don't have to worry about that as much. Limitations, it has a high reliance on proper representation of data. It can only predict a categorical outcome. With the k nearest neighbors, it doesn't need a separate training period. New data can be added seamlessly without affecting the accuracy of the model. Kind of an interesting thing because you can do partial training. That can become huge if you're running across really large data sets or the data is coming in. You can continually do a partial fit on the data with the k nearest neighbors and continue to adjust that data. It doesn't work on high dimensional and large data sets. We were looking at the breast cancer, 36 different features. What happens when you have 127 features or 1 million features? And you say, well, what do you have 1 million features in? Well, if I was analyzing the legal documents, I might have a tokenizer that splits the words up to be analyzed, and that tokenizer might create 1 million different words available that might be in the document for doing weights. Sensitive to noisy data, outliers, and missing values. That's a huge one with k nearest neighbors. They really don't know what to do with a missing value. How do you compute the distance if you don't know what the value is? The SVM works more efficiently on high dimensional data. It is relatively memory efficient. So it's able to create those planes with only a few different variables in there as opposed to having to store a lot of data for different features and things like that. It's not suitable for large data sets. The SVM, you start running this over gigabytes of data, causes some huge issues. Underperforms if the data has noise or overlapping. That's a big one. We were looking at that where the SVM splits it and it creates a soft buffer, but what happens when you have a lot of stuff in the middle that's hard to sort out and doesn't know what to do with? That causes SVM to start crashing or not perform as well. Decision trees. Handles non-linear perimeters and missing values efficiently. The missing values is huge. I've seen this in, the wine tasting data sets where they have 3 different data sets and they share certain features, but then each one has some features that aren't in the other ones and it has to figure out how to handle those. Well, the decision tree does that automatically instead of having to figure a way to fill that data in before processing like you would with the other models. It's easy to understand and has less training period. So it trains pretty quickly. Comes up there and just keeps forking the tree down and moving the parts around. And so it doesn't have to go through the data multiple times, guessing and adjusting. It just creates the tree as it goes. Overfitting and high variance are the most annoying part of it. That's an understatement. That has to do with how many leaves and how many decisions you have it do. The more you have, the more overfit it is to the data. It also, just in making the choices and how the choices come in, it might overfit to a specific feature because that's where it started at and that's what it knows. And it really is challenged with large data sets. They've been working on that with the data forest, but it's not suitable for large data sets. It's really something you'd probably run on a single machine and not across a data pool or anything. So that wraps it up today. Thank you for joining us at Simplilearn. For more information, please visit www.simplilearn.com. Get certified, get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.